Hey there, welcome back to lesson 7.4 where we are going to be rocking surface area in this video of a revolved solid. So what does that mean? Well, we saw earlier in this course that when you revolved a two-dimensional region, right, an area about an axis, we ended up with volume. Well, we could also find the surface area of that solid, right, which would be the area of the outer part of it. So what I'm showing here is we've got some kind of curve like this, and it's rotated about, in this case, the x-axis, and we get a vase-like thing or a vase-like thing. Our cross-sections are a little bit different here. They're actually things called frustums. More on that in a little bit, right? It's almost like you've got like a pie dish or a cone with its pointy part cut off, if you will. Those are the cross-sections. And so what we have is a formula that you need to get down, and this formula not needed for the AB or BC exams, but some Calc 2 teachers definitely going to be asking you to know this. So the formula is 2 pi times the integral from a to b of the radius, which is going to be the distance from the curve to the axis of rotation, like that, times ds. ds is this length right here, or that length right there. It's that little tiny arc length. So that would be ds, and this would be r. Okay, so what's this all about then? Well, writing it out a little bit further from here, you combine your knowledge of arc length and your idea of what the radius is, and you've got yourself a formula that's a little bit nastier to memorize. That's why I'd recommend you memorizing that to get to this. So we've got the radius, which in this case could be the distance from that part right there, no holes, so distance from the curve to the axis of rotation. In this case, that would be this part right here. If this is f of x, and this is the x-axis, this would be a distance of f of x minus 0. So you get f of x times ds. Remember, that's your arc length, which would be the square root of 1 plus f prime of x, all that quantity squared, times dx. That's it. Now, if you were to revolve this thing about the y-axis, right, vertically, what changes here? Well, what doesn't is that that's still ds. Your radius, now, if we keep things in terms of x, is just x minus 0. It'd be the distance from the curve, right, to x equals 0, which would just be the x distance. So if we translate 2 pi times the integral from a to b of r ds, that's 2 pi times the integral from a to b of x root 1 plus f prime of x, all that quantity squared. And of course, you've got your dx. Okay, so now, what I want you to notice here, and I put this little note at the bottom, is since the arc length can be in terms of x, we keep the integrand in terms of x, meaning it doesn't really matter that we're rotating this thing about the y-axis. It doesn't now make it in terms of y, because arc length can be in terms of x no matter which way you rotate. X is the radius. I'd rather keep everything in terms of x. The only time you change surface area in terms of y is if the function's in terms of y. All right, let's dive into a couple problems using this, and then at the very end of this video, we're going to go over where this formula comes from. It's pretty rad. Okay, let's take a look. So on to the next part. All right, so what we've got is, we've got f of x equals 2 root x, y equals 0, x equals 4, and x equals 9. That's our region. It's to set up and evaluate the definite integral for the area of the surface generated by revolving the given region about the x-axis. Okay, so 2 root x is going to look something like this. We're going to rotate that about the x-axis, like so. The region is going to be from y equals 0. That's down here. Do that in a different color. So that's the x-axis. And then all the way to x equals 4. Let's make that here. And then when you rotate it, x equals 4 to x equals 9, be here to here. When you rotate that, you're going to get just this part right here. So let's erase this away. All right, neatens it up. So we're going to get this piece right there. Let's dot it out. And now we've got this kind of three-dimensional object. So you're looking for the surface area of this thing. Okay, so how do we find that? Well, looking at this, I need the radius. The radius is going to be the distance from that curve to the axis of rotation, right? That's going to be r. Why do we need that? Well, write out your template. So it's from a to b of 2 pi r ds. Okay, well, the radius is going to be that curve, which is 2 root x minus 0. And you'll only ever be asked about rotating this about the x or y axis. Very, very rarely are you rotating it about other kinds of lines. So 2 pi integral a to b of r ds ends up being 2 pi. A is going to be 4. That's your x value on the left. 9 is going to be x, the upper x value. Then r is 2 root x. ds, remember that is the arc length. So that's going to be times the square root of 1 plus, now we need f prime of x squared. So I need the derivative of f, right? So I'm going to do that workout right here. So f prime of x, remember that this is 2x to the 1/2. So the derivative of that is going to be 1/2 times 2 is 1, x to the negative 1/2, which ends up being 1 over x to the 1/2, or root x. Now you're going to end up squaring that, right? So that'll be 1 over x. So to be very clear, this ends up getting squared, and root x squared is just x. Of course, we have dx. So that's your setup. That's it. From here, it's just about taking the integral. And the integral is actually pretty gnarly in terms of the first step. But once we get through that, you'll be okay. So we get the integral from 4 to 9. I'm going to factor out a 2 from that root x. Now, root x, because it's underneath the square root, I can multiply the x into the square root. So that'll be x times 1, which is just x. And then x times 1 over x, these x's will divide out, leaving me with just 1. Oh, it simplifies very nicely. So now the integral of this is not so bad. The square root of x plus 1, remember, you're looking at that like it's x plus 1 to the 1/2. The integral of that is not bad at all. So you're going to get 4 pi times, this will be x plus 1 to the 3/2. Division by 3/2 gives us times 2/3. And that'll be evaluated from 4 to 9. So now we're just up to evaluation. So 2/3 times 4, that ends up being 8 pi over 3, times. If I plug in 9, I'm going to get 10 to the 3/2. That's something special. Minus 8 pi over 3 times 4 plus 1 is 5 to the 3/2. Oh, man. That's not a very nice root at all. Okay, so now from here, all we're going to do is we're going to simplify. This would be fine, leaving your answer like that on my test, but some teachers want you to go further. This is the square root of 10 cubed, which is 10 root 10 times 8 would be 80 pi root 10 all over 3 minus, this is 5 root 5 times 8 would be minus 40 root 5, and I guess you'll have a pi in there, divided by 3. That's it. So that right there is your gnarly surface area. Okay, on to another problem. Here we go. Set up but do not evaluate the definite integral for the area of the surface generated by revolving the given region about the y-axis. Okay, so if we're revolving this about the y-axis like this, still the same region that we had before, but the difference here is that we're actually going to revolve it this way, right? So we end up with a region like this. And while you do have a hole in all of this, we're not finding volume, right? So that's perfectly fine that there's a hole going on in here. You got some kind of solid like that. You got the hole happening down there, but that's okay, right? We got this. We're just finding the surface area of it, and it still works the same exact way as what we did before. And we're finding the surface area of this piece right here. So we'll be in good shape. We'll be in great shape, actually. So looking from this, again, we're not finding the surface area of that inner hole part, only of this piece right here, if that makes sense. So only of this part, almost like the lateral surface area, that part and that part. So not finding the inner surface area, that inner hole, or of that outer edge, just of this piece here as it rotates around. All right, just want to be very clear. Here we go. So our formula is going to be 2 pi times the integral from a to b of still r ds. But now in this case, the radius is going to be the distance from here to there. Right? That is going to be our distance right there. And again, not finding anything in here, just out to this part right there, just that piece. So now what I'm going to do is I'm going to take 2 pi times the integral, and now we have our bounds, right? So we're going to be doing that from 4 to 9. And then we've got x, right? Because that's going to be our radius, that x value right there. Very nice. And then that's going to be evaluated times the square root of, well, again, we've got arc length, 1 plus, and I'll need f prime. We found f prime before, so f prime of x is equal to, well, now that's going to be 2 times, this is x to the 1/2. So the 1/2 is going to come out, x to the negative 1/2. The 2 and the 1/2 cancel, leaving you with x to the negative 1/2. All right, so that's x to the negative 1/2, all of that squared, and then that's going to be dx. And you can leave it like that. That's setting up and not evaluating. Again, I want to be very clear. We're not finding the surface area of this inner piece right here, right? We're only finding the surface area of that top part that's formed by this arc right there, just to make it easier. It would make it harder if you wanted to find the area of this part right on the inside. You'd have to add the surface area of a cylinder, in other words. Okay, so I'll leave it at that. Not so bad. I think it's pretty gnarly. And on to the why all of this works. So where does the surface area formula come from? Where does the surface area formula come from? So it actually comes from the idea of the area of this thing called a frustum. So think like a peanut butter cup or a pie dish or a cone, again, with its top lopped off, right? If we cut it off right here, you get something that's a frustum, this shape right there. The area of a frustum, through a lot of proof, and I've done the proof a couple times, it's very cool, you get is pi times the radius of the bigger circle plus the radius of the smaller circle like that quantity, times the slant height, which would be this height right here, that's L. Now, what we want out of all of this is to recognize that this is the cross-section of, well, basically all of these surface area pieces. So as this gets really, really, really thin, this L becomes basically ds. It gets very, very small. So L ends up approaching ds as this cross-section shrinks down. We get a super, super thin buttercup, if you will, or pie dish. And then what also happens is R1 and R2 approach each other to be the same length. So you end up with pi times R plus R, basically becomes all the same radius, times ds. And that becomes 2 pi r ds. Ah, but we don't just want one area of these frustums, we want infinitely many of them, right? So that would be the integral of 2 pi factored out times r ds. And we've done that a couple of times now where we've seen that as the formula. So I just want to show you where that formula comes from. I think it's pretty wicked cool. And that's it. I'll see you in the exercises. Peace.